AI is supposed to be getting cheaper. The models are becoming more efficient. The cost of generating an answer is falling. Smaller models can now do things that once required enormous systems, and yet the companies building the most powerful AI on Earth are spending more money than ever. So, why is AI getting so expensive? The answer is much stranger than simply saying GPUs are expensive. Because right now, two completely opposite things are happening at the same time. Using AI is getting dramatically cheaper, while building the most advanced AI systems is becoming dramatically more expensive. And once you understand why, you start to realize that the AI race isn't really just a software race anymore. It's a race to control electricity, computer chips, data centers, networking equipment, land, and even the power grid itself. Let's start with the part that seems impossible. A few years ago, asking a powerful language model to answer a question could cost significantly more than it does today. Stanford's 2025 AI Index found that the cost of querying a model with performance around GPT 3.5 on a standard benchmark fell from about $20 per million tokens in November 2022 to just 7 cents per million tokens by October 2024, a more than 280-fold decrease. At the hardware level, price performance has also been improving rapidly, with machine learning hardware costs falling roughly 30% per year and energy efficiency improving around 40% annually. So if AI is becoming cheaper to run, why are the companies behind it spending so much more? Because the thing becoming expensive isn't necessarily the individual answer you receive, it's the machine that has to exist before that answer can ever be generated. Think about a restaurant. The cost of serving you one extra glass of water might be tiny, but opening a restaurant from scratch can cost millions. Frontier AI works in a similar way. The expensive part is building the enormous computational infrastructure needed to train increasingly capable models and then serve them to millions of people simultaneously. Training a modern frontier model isn't like installing an app on a laptop and pressing run. It can involve enormous clusters of specialized accelerators working together for weeks or months, connected by extremely high speed networking systems, supplied with electricity, cooled continuously, and supported by teams of researchers and engineers. Estimates from Epoch AI found that the hardware and energy cost of the final training runs of frontier models has been growing about 2.4 times per year since 2016. Their broader estimates suggest the total development cost of major frontier models includes not just the final training run, but experiments, supporting compute, hardware, and research staff, and in their analysis of several models, hardware accounted for roughly 47 to 67% of development cost, while research staff accounted for roughly 29 to 49%. Energy itself was a smaller percentage of those estimated development costs, around 2 to 6%, but that doesn't mean electricity is unimportant. The amount of power required to operate these systems is enormous, and this is where AI stops looking like ordinary software. Software normally gets cheaper to reproduce. Once you've built an application, making a second copy doesn't require constructing another building the size of a warehouse. AI is different because the software depends on physical infrastructure every time it is trained and every time it is used. You need accelerators, servers, memory, networking, storage, electricity, cooling, and the buildings that contain all of it. And the biggest models need enormous amounts of all of those things at once. Epic AI has estimated that the power required for training frontier models has been roughly doubling annually, driven mainly by larger clusters and greater hardware usage, even as efficiency improvements reduce the power needed for a given amount of computation. That creates a bizarre situation where each individual calculation can become cheaper and more efficient, while the total amount of calculation keeps exploding. It's the same reason a more fuel efficient car doesn't necessarily reduce total fuel consumption if everyone suddenly starts driving 10 times more. And AI usage is doing exactly that. The International Energy Agency reported in 2026 that electricity consumption from data centers rose 17% in 2025, while AI-focused data centers grew even faster. The IEA expects global data center electricity consumption to double by 2030, and electricity use from AI-focused data centers to roughly triple over that period. At the same time, the IEA says electricity consumption per individual AI task is declining rapidly because of efficiency improvements. That contradiction is the key to understanding this entire story. AI is becoming more efficient, but we're using vastly more of it, and the companies building the infrastructure are preparing for even more demand. In 2025, five major technology companies spent more than $400 billion in capital expenditure, according to the IEA, and the agency expects that figure to rise by another 75% in 2026. The number is so large that the IEA says capital expenditure by just those five technology companies is now larger than global investment in oil and natural gas production. And these aren't abstract investments. They are physical things: data centers, servers, networking equipment, power systems, and other infrastructure. Alphabet, for example, reported $91.4 billion in capital expenditure for 2025, with about 60% going to servers and around 40% to data centers and networking equipment. Meta said its 2025 capital expenditure was expected to be around $70 to $72 billion and warned that 2026 infrastructure costs would continue to grow significantly as it expands capacity for AI. Amazon expects to spend around $200 billion in capital expenditures across the company in 2026, driven by major opportunities including AI, cloud computing, chips, and other technologies. These companies aren't spending this money because they suddenly forgot how expensive hardware is. They're making a calculated bet that access to enormous amounts of AI compute will become strategically important. And that's where the AI race becomes something much bigger than building a smarter chatbot. Imagine two companies competing to build the world's best AI model. One company has access to a huge cluster of cutting-edge chips, enough electricity to operate it, giant data centers, fast networking, and enough money to run enormous experiments. The other company has a great research team, but only a fraction of the compute. Even if both researchers are equally talented, the first company may be able to run dramatically more experiments, train larger models, test more ideas, and iterate faster. Compute becomes a competitive advantage. And once compute becomes a competitive advantage, companies have an incentive to buy more of it before their competitors do. That creates a feedback loop. More powerful models require more compute. More compute requires more infrastructure. More infrastructure costs more money. But that infrastructure enables new models that can generate more revenue, which creates the financial justification for even larger infrastructure projects. This is why the AI industry is building data centers at a scale that would have sounded absurd just a few years ago. And there's another hidden cost. Not every AI problem can be solved by simply buying another rack of GPUs. You need the electricity to power those machines, and electricity infrastructure takes time to build. You need grid connections, substations, transformers, transmission capacity, backup systems, cooling equipment, and often new power generation. The IEA's 2026 analysis says data centers are increasingly running into physical bottlenecks, including tight supplies of advanced chips and IT components, gas turbines, transformers, and the infrastructure needed to connect new facilities to the grid. In other words, the AI industry can have billions of dollars ready to spend and still have to wait for the physical world to catch up. That's a major reason why AI is beginning to look less like a pure software industry and more like an industrial infrastructure industry. But there's an even deeper reason costs can keep rising. The frontier keeps moving. Every time researchers make a more capable model, they discover new ways to push it further. They want models with better reasoning, longer context, better multimodal capabilities, stronger coding ability, better reliability, more tool use, and increasingly autonomous behavior. Stanford's 2025 AI Index reported that training compute for notable models was doubling approximately every 5 months, while training datasets were doubling around every 8 months, and the power required for training was increasing annually. The exact relationship between model capability and compute is complicated, and improvements in algorithms and hardware can offset some of the cost, but the overall trend is clear. Leading companies continue to scale the amount of computation behind the most ambitious models, and that creates a strange economic race. The goal isn't simply to make an AI model that is good enough, the goal is to make one that is better than everyone else's before the rules of the market change again. That means companies may deliberately spend enormous amounts of money today in the hope of gaining an advantage tomorrow. This is why you can look at an AI company's financial reports and see billions flowing into infrastructure even while the price of using AI services is falling. The business model depends on scale. If inference becomes cheaper, companies can offer more usage, attract more customers, and potentially make the technology available to entirely new markets. Lower prices can actually increase total demand. And when demand increases enough, total infrastructure requirements can still grow, even though each individual task becomes cheaper. This is one of the most important points in the entire story. Cheaper AI does not automatically mean smaller AI. In fact, cheaper AI can create a world in which people use dramatically more AI, causing total demand for compute and electricity to rise. The IEA's latest analysis essentially describes this effect. Efficiency per AI task is improving quickly, but adoption is increasing and more computationally intensive applications are emerging, including AI agents. So the amount of energy used by the whole AI ecosystem can rise even while the energy needed for each individual task falls. It's a little like storage. A phone can become dramatically more efficient at storing data per dollar, but if people start recording everything in 8K, suddenly they need even more storage than before. Efficiency changes the cost of each unit. It doesn't guarantee that total consumption will fall. And this brings us to the biggest question. Will AI eventually become cheap enough that these enormous infrastructure costs stop mattering? The answer might be yes, but not necessarily because AI companies will spend less. They could simply get much more useful computation for the same amount of money. Hardware continues to improve, model architectures become more efficient, software gets better at using chips, and smaller models can handle tasks that once required enormous frontier systems. Stanford's data already shows how quickly inference costs can fall. A capability that cost dollars yesterday can eventually cost cents or fractions of a cent. But frontier research may continue pushing in the opposite direction because once a capability becomes affordable, companies can afford to demand more of it. More reasoning, more agents, more context, more multimodal processing, more persistent memory, more interactions, more autonomous actions. The ceiling keeps moving. So maybe the real story isn't that AI is becoming more expensive. The real story is that we're building a machine that is simultaneously becoming cheaper to use and more expensive to build. And that distinction matters because it changes what the AI race actually looks like. The winners may not simply be the companies with the smartest researchers or the best algorithms. They may also be the companies that can secure enough chips, build enough data centers, obtain enough electricity, connect those facilities to the grid, and pay for the enormous infrastructure required to keep scaling. AI may have started as lines of code running on computers, but the frontier is increasingly limited by things you can physically touch: silicon, steel, cables, cooling systems, power plants, land, and time. And that's why the next stage of AI could be much stranger than the last. We used to think the biggest obstacle to smarter AI was finding the right algorithm. Then we learned that algorithms need compute. Then compute needed data centers. Data centers needed electricity. Electricity needed infrastructure. Infrastructure needed capital. And suddenly, the race to build smarter machines became a race to build an enormous physical world around them. So, is AI getting expensive? For the user sitting at home, the surprising answer is often no. Many AI capabilities are getting dramatically cheaper. But for the companies trying to build the most powerful systems on Earth, the answer is very different. The frontier is becoming a gigantic industrial project, and every new generation demands another leap in hardware, power, infrastructure, and investment. And perhaps the strangest part is that if this strategy succeeds, you may never notice how expensive the machine behind your answer really was. You'll type a question, wait a second, and get a response that cost almost nothing compared with the billions of dollars of infrastructure that made it possible. The AI could become cheaper for you precisely because the companies behind it built something unimaginably expensive in the background. And that might be the real paradox of the AI era. The smarter the machine becomes, the more invisible the physical world required to create it may become.